All right, so here I am on my Windows remote desktop protocol, viewing an Intel-based machine, and we're going to do this 122. So I'm going to create a program. Now, we should have Visual Studio installed on here. It's an older version, but it doesn't matter. So if I click this and then All Apps, I should now be able to scroll down to the V's and find Visual Studio 2019, and I'll find a folder full of shortcuts, and this is where you have to go if you want to launch programs here. And I think we want, all right, I'm going to have to go back here. We want x86 native tools for VS. Okay. I think I have to do it again. x86 native tools, okay. And Microsoft in its wisdom will not let me move this box to see behind it because that's Microsoft for you. Anyway, x86 native tools is here. This is where you write 32-bit code. It just looks like a command prompt, but you have to launch it from the shortcut to go in the right directory and have the right environment. So here I am. Now you don't have to stay here, but you have to launch it here. It's something like the working directory has to point to where the tools are or something like that. So let me shove this to the side and let's do make dir. I might already have it there. Let's see if I already have PE on this machine. And I don't. Okay, so I make dir C:\PE. All right, and now I go there. And now I notepad hello.cpp. All right. And now I'm going to say, yes, I want to create a new file, and I want to shrink this window over to the side a bit. All right, that's pretty good. All right. I'm just trying to make a simple program so we can see how it works. So here's about the simplest program you can have. It's just a hello world program. So I put that code in Notepad. And all this is going to do is print hello, and then come back using IOStream, which is the C++ library or handler or whatever you call it, to run that code. So now we're going to compile it. You compile stuff with CL, and it often tells you to put in these switches. I forget what they do, but it's pretty common. You have to put in that EHSC. And then you compile hello.cpp. And you can see it created hello.object and hello.exe. If you do a directory, you can see that. The object code is compiled assembly language code for the source code. And then when you connect all the libraries and everything, you get the full executable, which is much bigger. So now I can run it, hello.exe, and it prints hello in return. So it isn't doing anything very exciting. It's about the simplest executable. And we're just going to analyze how this executable works so we understand how Microsoft Windows executables work. So let's look at it in PE view. Here's PE view, and I'll accept whatever the conditions are. All right, now I'm going to open C PE hello. Open. All right. So here you see the whole code in raw hex. And let me see if I can make the font bigger. I think that would be better. Font. I'll just make it bigger. Good. All right. So here you see MZ is the start of all Windows executables. It always has this message: this program cannot be run in DOS mode. And this whole mess up to here is the MS-DOS header from the start down to there, which is a useless appendix, no longer used anymore. It's the first page, 256 bytes. At the 256th byte starts, or I guess a little bit different, F0, a little bit before that starts the PE, portable executable header. This is what is the header for all modern Windows operating systems. And that contains the actual header that's used. And if you scroll down a little bit, let me see if I can, there, I can do it this way. You'll see the text.rdata.data.reloc. Those are the headers for the individual data segments. And so you can scroll through it this way and examine it that way in raw hex. But for your convenience, you can also look at it here. Here's the image DOS header. Here's the MS-DOS stub program that I just pointed out. Here's the image NT headers. This is the one that starts at PE, the portable executable header for modern code. And then you have the section header for the text section that tells you how big it is and where it starts. These are headers. This is what we saw, just a few bytes storing where these things are. And then you have the actual text section down here that includes the assembly language instructions. So it's all pretty unreadable gibberish. It's not readable English. Here's the R data, which is again a bunch of pointers pointing to things because this is the import table. But down here you'll see some readable text, which has something to do with the name of functions and such. And if you go to data, it's here. And here's the relocation section, which includes the way to relocate this thing in memory, because this is compiled by default to be relocatable, position independent executable. So all the hard-coded addresses in the compiled code are indicated down here how to change them if it gets relocated in memory. And here's the import address table, which shows you all the Windows API functions it's using. And as you can see, even the simplest possible program that just prints hello world is using dozens of API calls. It's crazy how complicated it is. These are all in kernel32.dil, which is not the Windows kernel. It's the userland component you use to control the kernel. Remember the general rule in Microsoft, everything is always named the opposite of what it is. So the thing named kernel is not the kernel. The actual kernel is NTOS kernel.exe. This is the userland component you use to control the kernel. So this is the way Microsoft wants you to do things by calling this to do things like flush a buffer, get process heap, get a string, and so on. All right, let me see what my project instructions said. I think it just goes through this stuff so you understand the components, the MS stub, the NT header. And one thing in the NT header was the time date stamp. That shows you the time this program was compiled, although not all compilers fill it in, and it doesn't have to be filled in accurately, so you can't necessarily trust it. But under normal conditions, if you compile your code with a normal compiler, it will show you the time and date that it was compiled, and a lot of malware analysts use that to guess what nation it was in, because they figure you'll figure out from the time zone when that program was compiled, when it was working hours. Then you've got the image base, which is in the image optional header. Let me go back there. Here you see, right here it is. Image base is always 400,000. Every Windows executable thinks it's running at the location 400,000. But it's not, of course. It's relocated to another place because you could only have one program running at 400,000. And so the size of images here in the import table is the relative virtual address of the import table. Let me go here. RVA is the relative virtual address. Maybe it's down here. Yep, here's RVA. Here's the relative virtual address of these things. This far from the image base is the export table, the import table, the resource table, and the exception table. These are tables of pointers. The import table, of course, shows it what libraries are being imported. All right. There's the import address table. You can see it here. Keep going down. I guess, all right, enough of that, I think. And then you have the section headers, which I talked about. Let's look at some of these section headers, like the text section. It tells you the size of raw data, the pointer to raw data. And so what you can do, the name is limited to 8 bytes. The virtual size is the size of it in memory. The relative virtual address is where it's going to be compared to the base. So the relative virtual address is 1,000. So this is going to be at 400,000 plus 1,000. And let's take a look at that. This is the text section. So if I go here, you can see it's showing you the relative address here of 400. That's relative to the base. And you can tell, if you go back to the original raw view, notice this starts with 55 8B EC. If I go back to the raw view here, and now go down to 400 1,000, well, I guess oh, that's right, not going to be that easy to find it there. Yeah, the relative virtual address is in this packed thing, not how it's actually laid out in memory. Anyway, that's the plan here. The pointer to raw data shows the location within the exe file. All right, on disk. So the memory layout, when it actually lays it out in the program, it's going to take these sections that are all jammed together in the exe on disk, and it's going to lay them out in memory. The image base will be here at 400,000, the text will be here, our data here, data the relocation there. It's going to construct this by taking these sections and copying them into memory, spaced out. And then it won't really be at 400,000. It'll be at a virtual address of 400,000, but the real address will be relocated by the operating system somewhere else. And you can see the memory map if you open it in Ollie debug. So let's do that. If I launch Ollie, that's why I made a 32-bit program, by the way, not a 64-bit program, so I could analyze it in Ollie. Now if I open CPE hello, all right, now I'm going to again adjust the font. I think it's appearance, fonts all OEM. That's somewhat better, but I think I can do better. Options, appearance, fonts. I'm going to change the OEM, and I'm going to change it to be Lucida, bold, bigger. Okay, now we can see what's going on better. This is the program that's going to call hello, and you can view the memory map. And when you do, you'll see how it looks in memory. Let me change the font again. Appearance. I like how when they chose font all, it didn't believe me. There we are. So here you see hello, the PE header, then the text, our data, data, and relocation. And notice they're not really at 400,000. They're at 520,000. This is from address space layout randomization. Every time you launch it, the operating system will randomly move it, and that's why it has this relocation section to help do that. It thinks it's running at 400,000, but that's a virtual address. The real address is moved by random base. So there's the sections in memory. And let me see what else I wanted to point out from the instructions, which I'm having trouble getting back to. Here we are. All right, so the import address table we already looked at. This had a series of functions you could load, and it has addresses for them all. And that's what you're seeing. So now there are various programs here to fix. Here you'll find it has 4 sections. So this has an extra section that you don't see in the file we examined above. So that'll be the flag here. Here's a file that's broken, and you can fix it using CFF Explorer. CFF Explorer is very nice. Let me just demonstrate that. That's a good thing to know. Let me close these things. I'm done with Ollie. Exit. All right, and I'm done with PE View. Let's open it in CFF Explorer, which is really nice. It's another way to see these things. So if I open CPE hello.exe, all right. Now here you see the same information you saw before laid out another way. You've got the import directory here showing it imports kernel 32 and relocation directory, the debug directory. And up here you have the file header and the optional header. Here's all the API calls it makes. Or no, this is the base of code and stuff. This is very much the same kind of information you saw on the other thing. The thing, though, that's useful about this is if one of these numbers is invalid, it will turn red. So to get the second flag here, you have to fix a broken program. I took a program and I broke it by changing something important in a hex editor. And if you use CFF Explorer, you'll be able to quickly spot what value is wrong. And then you can deduce what the right value should be. And then you can fix it. So fix it and run it. Here's another one you have to fix it and run it. And I have some hints to help you do that. So that's all I wanted to show you. You get to practice doing this to look at the headers and see what can go wrong. So let me just stop this video.